Okay. Well, okay. So today, what I would like to show you is the Brunn-Minkowski inequality, which is a tool in convex geometry, which has then several applications, which are not so easy all to explain, but at least I would like to give you some ideas of how to prove this inequality and what can you do with it. So we start. So the general question is the following. So let's say that I have two sets, A, B, which can be sets even in a Rn, or they could be subset of actually Zn when you are in the additive setting. So or we're gonna just consider actually Z, so subset of the integers. And so the first question you want to understand is, given the sides of A and B, how big is the set A plus B? So here A plus B is nothing else than the set composed by all the elements of the form A plus B, where little a is in capital A and little b is in capital B. And in addition, so this is, if you want, question one. And question two is, if the sides of A plus B is not too big, what can we say about A and B? So this is like a very general, vague question. So let me start maybe in probably the most classical and easiest case, which is, so we're going to consider actually the case A equals B first. And let's say that A is just a subset of the integers. Okay, so I just have and A is finite, just a finite set. So in this case, what we want to understand is the sides of A plus A. So I have a set, and the sum with itself. So this is A plus A prime, A and A prime A. Okay, so it's very easy to estimate from below the cardinality of this set in terms of the cardinality of A. The point is the following. So first of all, let's say without loss of generality, I can assume that A, so I can all these properties don't depend on translations. So I can always translate my set in such a way that it starts from 0 and is in the half line, the positive set. So I have my set of integers, and this is 0, let's say 1, 2, capital M. And let's say that 0 is in A, then others are in A. So I can assume that A is of the form 0, and then other elements up to M. Maybe there is 0, 2, 15, something. So up to a translation, I can always assume that it starts from 0. So you see that A plus A is going to contain, for sure, A itself, because you do, for every element, you can take A prime equals 0. So when you do the sum with 0, you get A itself. Union, when you take the largest one. So you get the set M plus A. So you take A and you translate it by M. So you get a second copy of A here. So which is going to go up to 2M. And so how big is the cardinality? So cardinality of A plus A. Well, so you have the cardinality of A here, the cardinality of M plus A here, which is the same as A. And then there is one element in common, which is M, which is counted both here and here. So you get that this is greater or equal than twice the cardinality of A minus 1, because of one element. And actually, so this is an easy inequality, and this is sharp. So this is sharp. And so there is actually, I'm going to show you an if and only if characterization. So in a sense, now you can ask yourself, so the first thing whenever you have an inequality as a general fact is you ask yourself, is this inequality sharp? So is this a trivial bound or is actually satisfied by some set? And whenever I have equality, what can I say about the set itself? So the first thing I can say is that suppose that A is of this form: 0, k, 2k, capital N k, for some k positive. So this is an arithmetic progression. Okay, so you just take the same multiples of the same number k. Well, then you can easily see that A plus A, when you start to do sum of elements like this, you're always going to get multiple of k's, and you go all the way from 0 until 2nk when you start to do all the possible sums. And so in this case, you see immediately that the cardinality of A plus A is, well, you have 2n plus 0, so you have 2n plus 1, and the cardinality of A, since you start from 0, these are n plus 1 elements. And so the cardinality of A plus A is equal to twice the cardinality of A minus 1. So you cannot prove anything better than that. Actually, you can ask yourself whether this is the only possible example. So the question becomes now the converse. If this is an equality, is it true that A is an arithmetic progression? So let me cancel here. So conversely, if the cardinality of A plus A is equal to twice the cardinality of A minus 1, then A is arithmetic progression. Should I briefly repeat, maybe? I didn't do much. I just defined what is the sum of sets with itself. And I just show that the cardinality of the sum is always greater or equal than twice the cardinality of a set minus 1 for a finite subset of integers. And you have equality when A is an arithmetic progression. And now we want to show that whenever the cardinality of A plus A is equal to twice the cardinality of A minus 1, so the equality holds there, then A is an arithmetic progression. So the proof of such a fact is actually pretty easy. It's just by induction on the number of points. So this works by induction on the cardinality of A. Well, the cardinality of A is 1, then it's trivial. If you have only one element, there isn't much to prove. And for the general case, so the inductive step, you just argue as follows. So let's say that you have your set A, which again you can always assume that it starts from 0. So let's say A is something like 0, and then there is an element that I'm going to call M, and then there is another element M tilde. So this is the largest element, and this is the second largest. And then you just consider this subset A prime as a subset of A. And now we count. So we're going to use this to show that actually, if the cardinality of A plus A is equal to twice the cardinality of A minus 1, then the same is true for A prime. And then for A prime, we apply the inductive hypothesis. So let's look at this. So A plus A contains the following set. So you have A prime plus A prime, because you take every possible couples when both elements here are in A prime. Then you can consider in A plus A you have also M plus M tilde, which is not here. And then in A plus A you also have twice m tilde, m tilde plus m tilde. So you have at least 2 more elements in this set with respect to this set. There are these 2 extra. So this means that the cardinality of the cardinality of A plus A is greater or equal than the cardinality of A prime plus A prime plus 2. Now this is equal to twice the cardinality of A minus 1 by assumption. And here we always know that the inequality is true. So we apply the inequality to A prime, so this is greater than 2 the cardinality of A prime minus 1 plus 2. And now the cardinality of A is equal to the cardinality of A prime plus 1, because we just remove one element. So this is twice the cardinality of A prime plus 2 minus 1. Cardinality. Wait, I'm losing one element. And no, wait. To the cardinality of A minus 1 to the cardinality of A prime minus 1. Minus 1. Oh, what is the mistake now? I lost one element. No, that's fine. Sorry, no. What am I saying? No, okay. So this is equal to this. Sorry. That's fine. So this is equal to this, which means that all inequalities are equalities, which means that in particular here I had equality. And so this means that here the cardinality of A prime plus A prime is equal to twice the cardinality of A prime minus 1. So, right, so this subset satisfies the same assumption. So then you apply the inductive hypothesis and you deduce that this guy is an arithmetic progression. But then you can do the same with this other guy. You just keep the 0 out. So this is an arithmetic progression, this is an arithmetic progression, and then you put them together. This has to be the same arithmetic progression. So here you use induction, A prime arithmetic progression, and then you conclude. You conclude just by doing this with 2 sets. So, okay, this is like a baby model for this kind of inequality which study the structure of sets. So actually there are there is a lot of research actually in this in the field of additive combinatorics. Well, people try to understand more in general, so not the equality case, but they ask more in general, okay, if I take A plus A, and I know that the number of elements is not too big, what can I say about the structure of A? So in general, A plus A could be huge, because if A has no structure, the sum, whenever you do a sum, you get a lot of extra elements. Actually, you could go, in some sense, you have to, how many elements you have here? You see that here you have something like A prime, A plus A prime. So here you have, let's say, if the cardinality of this is capital N, then you have n elements here, you do all the possible sum, you get something like n square. So you see it's a huge number. And here we're like just saying that the cardinality is twice. Okay, so there is a difference between 2n and n square. And actually, so already, if someone tells you, okay, the cardinality of A plus A is less than 100, the cardinality of A, which is way worse than this, then if A has a billion of elements, A cannot be anything. It must have some structure, because otherwise it would have 1 billion square. So once you start to try to understand this structure of sets, actually the structure of this kind of sets, this becomes a very non-trivial problem. Why people should even care about this? Okay, if you do number theory, you can be interested by itself. But the funny thing is that if you do analysis, you can be interested too. So for instance, there is people working in what is called harmonic analysis and also geometric measure theory are interested in the following. So there is a very famous problem which is called Kakeya conjecture. Which say the following. So if you give me a set E, let's say in R3, and you know that for every direction there exists a segment of length 1. Let me call it sigma. So for every direction V, there exists a segment sigma V of length 1 such that sigma V is contained in E. So you give me a set which has a segment in every possible direction. Then what the result says is that, okay, we'll not define what this means exactly, but the dimension of this set is 3. So this has to be a 3-dimensional set in R3. It cannot have a dimension smaller. So for instance, it cannot be, okay, a trivial lower dimension will be a surface, it's dimension 2. But the point is that you can construct fractals which have every dimension between 0 and 3. And the Kakeya conjecture states that if you know that you have a segment in every direction, then the dimension has to be exactly 3. This is known in dimension 2, and is like a big, big open problem in dimension 3. Like it has been, people have been working on this for 100 years. Because then it has application in Fourier analysis and partial differential equations, if one could do that. And at the moment, there are like lower bounds. So people know that this is greater than, for instance, 5 over 2. They could prove that. Okay? So they went up slowly, and they went, yeah.
Are they expecting positive Lebesgue measure there?
No, there is a counterexample. So it's known that a set which contains segment in every direction could have 0 measure. So it doesn't have to be a full measure. But the conjecture is that still it has to be 3-dimensional. And so people are really trying to go up. And then when some of the proofs use this kind of structure, because in some sense, you say, OK, if I have a segment in every direction, it means, for instance, that I have, you can think that, let's say, you take 2 planes, and they have segments pointing in almost every direction. So I have, let's say, every segment. So this is a 3-dimensional picture. So you take the extremal points of your segment. You say, OK, if this, I know that if this point is in E and this point is in E, also the middle point is in E. Right? So this would be like taking a point, A prime, and then you take A plus A prime over 2, which is just taking the set I had there and that's just divided by 2. So you see that looking at the structure of sets and trying to estimate how big has to be the set of, if you want, the midpoints, is a question which arises in problems completely different. So this, if you want, is the discrete version of problems to try to understand how big, if you give me a set of points on this plane, a set of points on this plane, how big has to be the set of midpoints. Because then if you can estimate this, then you get information on how big is your set. So this is just to show you why you can be interested in trying to, on the one hand, to prove lower bound, so to prove something like this. On the other hand, well, you want also to understand the structure, to understand how the set looks like. So that's the converse. So this was I just wanted to show you in this baby model, so A equal B and Z, the additive case. Now I want to pass to the continuum case. So the continuum case means that we're going to consider the case of R or Rn. So let's go to the continuum case. So let's do first the case of R. So in the case of R, what do we have? So I'm going to consider 2 different sets now, A and B. And without loss of generality, I can assume, so I can always translate my sets. So I can assume, so A and B are going to be compact sets. So let's say closed and bounded. Okay. Well, also generality, I can assume that the maximum of A is 0 and the minimum of B is 0. So I have the origin, and I can assume that my set A is somewhere here, and my set B is somewhere here. And now I want to understand A plus B. So if you want, this is more a lemma than a real theorem. It's very easy. The measure of A plus B is greater or equal than the measure of A plus the measure of B. And the proof, well, this just follows from the fact that A plus B contains, so you can take 0 here and any element in A here. So you can take always A plus the element 0, because 0 is in B. Or you can take 0 in A and have any element in B. 0 plus B. And now these two sets, so this is the same as A, and this is the same as B. And now these two sets are almost disjoint. They just have a 1 point in common, because they have the origin in common. But the origin has no measure, just 1 point. So you get immediately that the measure of A plus B is greater or equal than the measure of the A plus the measure of B, because these are almost the same set. Okay? So in one dimension, this is the Brunn-Minkowski inequality. Although is more an exercise than anything more. So the things start to become interesting when we go in higher dimension. So in higher dimension, let's try to understand what can be true. So the first question you may ask yourself is, well, is it true, for instance, can I prove this inequality in higher dimension? Can I prove that if you give me two sets in a Rn and you start to take sums, the volume of the sum is greater or equal than the sum of the volumes? Okay, let's do an example. Let's start with an example. I'm going to take A to be the ball of radius little r centered at 0, and capital B to be the ball centered at the origin of radius capital R. And now I look A plus B. So A plus B, what is? This is the set of couples x plus y, such that x is in A, so modulus of x is less than little r, and modulus of y is less than capital R. So when you start to take sums of elements like this, the sum is going to have modulus less than little r plus capital R. So this, of course, this is contained in the ball of radius, the sum of the two radii. And actually, you can immediately see that you can always generate everything. So actually, this is exactly the same of B. It's a very easy exercise to see that this is the same as this. Okay, so what happens in this case? The volume of A is going to be equal to the volume of the unit ball, measure of B1, times r to the power n. The measure of B is the volume of the unit ball to the times r capital R to the power n. And the measure of A plus B is equal to the measure of the unit ball times times little r plus capital R to the power n. And if you do the sum of the volume, well, it's actually true, okay, that this is greater or equal than the sum, but that's not very sharp. I mean, in this case, this is, I mean, with respect to this, you get something completely different, right? I mean, you don't have, in the case of, usually, at least you would like to inequality, which in general maybe is a inequality in some case. So you see that, for instance, even if little r is equal to capital R, the volume here you get r to the n, right? This is B1 twice r to the n, and here you get twice little r. So you get the volume of A plus B is 2 to the power n. B1 are to them. Okay? So these are different. But there is one thing which is the same. So how can we make this an equality? Well, so we cannot just add the volumes, doesn't work. But you can see that if here in the volumes you take a power 1 over n, then things works. So if I take the volume of A plus B 1 over n, this is equal to the volume of A 1 over n plus the volume of B 1 over n. Because this is the quantity which is proportional to the radii. So the radii are the one which adds up. It's not the volumes. So in some sense, you need to take a power 1 over n to the volumes to make them one homogeneous. And then these are the right quantities which adds up. So you get this fact for bolts. Whenever you take two bolts, you have this relation. And so the Brunn-Minkowski inequality is the inequality that tells you that you always have one inequality there is always true. So the theorem Brunn-Minkowski say the following, that the volume of A plus B 1 over n is always greater or equal than the volume of A 1 over n plus the volume of B 1 over n. So that's the first thing. And actually Brunn-Minkowski tells you even more. Tells you that the equality holds if and only if A and B are both convex and they are homothetic. So the only way you can have equality here is when you take two convex sets which are the same up to a translation and a dilation. So for instance, in that case you have equality because you took two bolts. Or you take two ellipsoids, the same ellipsoid, just maybe one is dilated, and you get equality. And these are the only possible cases. So homothetic convex sets. So it's actually funny that it's called Brunn-Minkowski because they didn't prove this. I mean, they proved only the theorem for the convex case. And even the characterization for the equality case, they just did it in the convex setting. So there was first Brunn who proved something, and then Minkowski proved something, but then really Brunn-Minkowski was proved later. But they got the name attached to it. Sometimes mathematics goes like this. Okay, so this is an inequality which is very useful. And the proof of this inequality, there isn't for it. So very often when you prove inequality, sometimes you can prove them by induction on the dimension. This inequality, unfortunately, doesn't work like that. But there is actually a pretty elementary proof of this, which is not the original one, which I can try to describe to you. And the idea is the following. First, you prove it for boxes. And then you prove it for finite union of boxes. And then you say every set is a limit of, cannot be approximated by a lot of boxes. So if you prove it for arbitrary number of boxes, then every set is going to be a limit of boxes. So the real point is to try to understand what happens for boxes. So this means the following. So case 1, A and B are boxes. So this means that I have my set A, my set B, and I want to understand the volume of the sum. So let's say that I'm going to call my axis, let's say A1, A2, A3, the three length. So these are parallelepipedi which have the axis parallel. And then here I have B1, B2, and B3. B2 and B3. So what is A plus B? When you do A plus B, well, it's actually pretty easy to see that you get, again, a box. And what are the three sizes? Well, here on this axis you get A1 plus B1. On this axis you get A2 plus B2. And the third one is A3 plus B3. Right? And okay, I did it for 3. You do for n. I have a problem to draw n-dimensional objects. So you can, of course, do with n axis. So let's try to see why so the first thing you should do whenever you have an inequality, you want to prove something, is to try to see why the inequality is true in one simple case. Because that usually gives an inspiration of. So the key point is you may ask why even that inequality is true. I mean, like, and usually the way to prove this, to believe that this inequality is true, is to prove it in a model case. And this is like the model case, because it's very easy to compute everything here. So what is the volume of A? The volume of A is just the product from 1 to n of the axis, the sides AI. The volume of B is the same, n of the BI, and the volume of A plus B is the product of the AI plus BI. Okay, so now what I want to estimate, so my goal is to prove that this inequality is true. So what I'm going to do is actually to divide here. So I'm going to consider the quantity A 1 over n over A plus B 1 over n plus B 1 over n A plus B 1 over n. I want to prove that this quantity is less or equal than 1. So let's write down. This is the product over I of the AI 1 over n divided by the product of AI plus BI 1 over n plus the same with the BI. AI plus BI 1 over n. Okay, now these products, I can just put them together as a unique product. So this is the same as if I do the product of AI over AI plus BI 1 over n, right? Just do them. And the same there. The product of BI AI plus BI 1 over n, product up to n. Okay, now I hope you remember, you saw that whenever you have, what is this? So this is a product of non-negative numbers to the power 1 over n, which is called geometric mean. And the geometric mean is always less or equal than the arithmetic mean. So this sum is less or equal if I do 1 over n, the sum over I of up to n of AI plus BI. And then I have the same for the second one, from 1 to n of BI AI plus BI from the second term. But now you just put the sums together, term by term. What you have? AI over AI plus BI plus BI AI plus BI, it's 1. And then you sum them up from 1 to n, so you get n, but then you have 1 over n in front, and you get 1. So this is 1. Okay? And actually, this case already you can see the equality case. So from this model case, not only you see why the inequality is true, there is an arithmetic geometric inequality behind it, but you also understand the equality case. Because the only point from here to here where I lost something is in this step. That's the only moment where I had an inequality. All the rest are equalities. And when I had the inequality, it's because I use AMGM. But, so, okay, one has to prove it, but you can, it's not a difficult exercise to check when the arithmetic geometric inequality is equality. You can have equality, so this is not difficult to prove, if you want, as an exercise. So there is the following fact that if 1 over n sum of the lambda I is equal to the product of the lambda I 1 over n, where lambda I are non-negative numbers, this implies that the numbers are all the same. That's the only moment where you have equality. So then you can trace back this. So you say, okay, what happened if this was equal to 1? It means that at this step I had equality, which means that at this step all these numbers were the same. And once you get that all these numbers, so if the measure of a1 over n plus b1 over n was equal to a plus b 1 over n, then you will deduce that ai plus bi is equal to aj plus bj for every I different from j. And then you just put things together, you do the product, and you see that this implies actually that ai is like lambda bj for some lambda positive. So one is a multiple of the other, which means that the two cubes were one in the direction of the other. So the axes are multiples. Otherwise, you will lose some. You will lose something in this inequality. So this is. So what we did here, we proved this inequality in the case of boxes, and we saw even the equality case. Well, the convexity is trivial because boxes are convex, but you can prove equality. So this is the case of boxes, and let's start to look why the general case is true. You have any question up to now? Everything clear? Okay. So maybe let me cancel here. So the general case is actually just a smart trick for this inequality. So general case is by induction on the number of boxes in A union B. So in a sense, A is a finite number of boxes, B is a finite number of boxes, and you count how many boxes you have, and then you do by induction on the number of boxes that compose A and B, the sum of them. So whenever I can remove one box from them, by inductive hypothesis, I know the result is true. Okay. So I have this case where A is something like this. It's composed by maybe boxes around. I don't know, something like this. And so this is my set A. Is a union of stuff like this. And then you have B, which is somewhere else. So this is my B, which is another union of boxes. Well, of course, maybe at the end, your sets are going to be, I mean, you can always do like, yeah, maybe they're going to be packed at some moment, the boxes. Some are full. Well, actually, so let me, well, actually, okay. You do actually the following fact. So you do boxes, and you can take all the you can do even a for the simplification, you can assume that all the boxes are like, so more than taking them randomly, actually. The best thing is to take just a grid in a ren, let's say, and then, so you start, your set, actually, yeah, it's easier if I do it this way, right? So let's say my set A is something like this. These are all the same, even if from the picture it doesn't seem. So these are, yeah, let me just do it this way. It's also easier to draw pictures if I do with a grid. So you just do a grid here, the same grid here for B, and you keep coloring some of them. Okay, so this is A, and this is B, the colored boxes. Okay, so we are doing by induction on the number of boxes, and so it means, so I know, let's say that I know that if I take any set which has one box less than the number of boxes which are in A and in B, then the result is true. So what I can do, I just do the following. So I just take one of the hyperplane in such a way to split my set A in two parts, A plus and A minus, just to have some boxes on the right, some on the left. I need at least one on the right, just to lower the number of boxes. So I choose this one. I can always do this if I had at least two boxes. I can always put one on the right, one on the left. So I cut my sets. And then I'm going to cut B, but I have to cut this in a smarter way. So I'm going to cut with an hyperplane, which is not going to be necessarily passing through the grid. So maybe it passes here, with the following condition. So let me call this, so this set on the left is A plus, and on the right is A minus. And then I cut with an hyperplane, and I get B plus and B minus, where these are my boxes. And I have this. Scissors. For every grid, okay? And now so how do I choose this hyperplane to cut here? I'm going to choose the hyperplane with the following way. I go on that the fraction of volume of B, which is on the left, is the same for A and for B. So I can always start to move this hyperplane and then stop exactly where the volume on the left is the same on both cases. And now, without loss of generality, you can always assume that this is, let's say, x1 equals 0, the hyperplane x1 equals 0, and the same here, up to translate the coordinates. And now the proof is almost automatic because you just use the following, that A plus B. So when you do the sum of sets here, A plus B contains A plus plus B plus, and contains also A minus plus B minus. A minus plus B minus. And whenever you do sums, so you see if I take an element here and an element here, the element that I get is something which is on the left of the hyperplane x1 equals 0. The first coordinate is going to be negative. If I take a point here and a point here, I get a point which is on the right of x1 equals 0. So these two sets are disjoint. And this is why I get this inequality. Then I apply the induction hypothesis on this case and on this case, because the number of cubes here has gone down by at least one. Because here I have one less cube at least and one less here. Maybe here not, because I cut. So maybe by cutting, I didn't decrease the number of cubes. So here you apply the induction hypothesis, that you get A plus 1 over n plus B plus 1 over n power n, and the same for the second one. And then here, use this Hughes relation. So that's why you chose the volume right, because now this is nothing else. So you can take a factor out. This is A plus 1 over n, 1 plus, and this is the ratio B plus over A plus 1 over n to the power n. But you see that B plus over A plus is equal to B over A. So here you can remove the plus from this ratio. And you can do the same for A minus. In the second term, you get the same, exactly the same. A minus times 1 plus B 1 over n, A 1 over n, n. And then you just, these two terms are the same. And volume of A plus volume of A minus, wait, there is no 1 over n here, because there was 1 over n and n. So volume of A plus volume of A minus is volume of A. So here you get volume of A multiplying 1 plus B over A, 1 over n power n. And if you put A inside, you are this is exactly Brunn Minkowski. Right? You put A inside, you get to A1 over n plus B1 over n power n. And then, so we prove that for finitely many boxes is true, but you can take as many boxes as you want, so you just approximate every set. Okay, so this proof is pretty elementary in some sense. And proves an inequality which is used for a lot of stuff. So what I would like to show you is why people even care about Minkowski. You saw something already in the Kakaya setting. So the equality case is more tricky here. If you want to prove that the equality case, so that you have equality if and only if the sets are convex and homothetic, that's more difficult. But let me show just an application of this. So application is a very fundamental inequality in analysis, the isoperimetric inequality. The isoperimetric inequality is the following. You give me a set, think in the plane or in a RAN, whatever. Very nice, smooth. So E is smooth and bounded, all there you want. So the isoperimetric inequality tells you that the perimeter of the set, so by perimeter I mean the total surface area. That I don't know how many you saw, I'll probably define, but think if it is in the plane, this will be just the length of this curve. If you are in higher dimension, you have to define probably what is the surface, but it's the intuitive things, at least for most sets. So the perimeter of E is greater or equal than a constant, which is n times the volume of the unit ball to the power 1 over n, and the volume of E to the n minus 1 over n. So the perimeter of a set controls how much volume you can put inside. If you give me some perimeter, you cannot put too much volume. So the power so this is just a number, which depends on the dimension. This exponent is natural, because if you take a set E and you dilate it, you consider lambda E, you see that the perimeter of lambda E is equal to lambda to the n minus 1, the perimeter of E. Right? The surface area dilates like dimension to the n minus 1, just because it's a n minus 1 dimensional object. While the volume of lambda E scales like lambda to the n times the volume of E. Right? So the only way this inequality can be true for every set is if you put this power, because this power is the one which, if you put a lambda, then it's just gonna kill the lambda. Right? You put the lambda, the lambda falls out, and because of this power you can simplify them. So that's the only possible power. So this inequality, why this inequality is true? So let's prove it. So the proof is a corollary of Brunn-Minkowski. And the way to prove it is this. So we have to understand what is the epsilon neighborhood of a set. So let me redraw the picture. I have E. And now I'm going to consider the following set. E plus B epsilon 0. So I'm going to do the sum of every point in E with an arbitrary point which is in the ball of radius epsilon centered at 0. All right, so this is the sum of x plus y, x in E, y in B, so normal y less than epsilon. So what do you get? In some sense you have to think in this following way, right? For every x, I can take y, an arbitrary point in this ball. So I will get for this x plus y it will be this ball. And now you start to move x around. And as x varies, you're going to get, in particular when it is on the boundary, you're going to get this. And then you move it around, and you get, so as x, it's like taking a disk and rolling it out around. At the end, you're going to get all of this. Complete. So this is going to be E plus B epsilon of 0. okay? Which is nothing else than the epsilon neighborhood of your set. So every point which is a distance at most epsilon by E. That's exactly what you get. So this is the epsilon neighborhood of E. Okay, so I think time is almost over. So what can we say about this set? Well, we know that the volume of B of the epsilon neighborhood to the power 1 over n is greater or equal than the volume of our set 1 over n plus the volume of this ball, which is epsilon volume of B1 1 over n. That's the volume of the ball. On the other hand, what can we say about this? Well, okay, the volume of E plus B epsilon 0 is going to be what? Well, you have all the points which are in E, so you get EA. Then you have the volume of this strip. The volume of this strip is something like this. So you have the length of this times epsilon. And okay, it's true that your set is not exactly flat. But in some sense, the fact that it's not flat just gives you lower order terms in epsilon. So locally, you have to think that your set is super smooth. So when you have the set and epsilon is super small, then locally, when you look around, this looks almost flat. So this would be like if this was flat and this was like a rectangle. For epsilon very small, you're going to get epsilon, then there is going to be correction, but these are going to be lower order terms. So you get epsilon times the perimeter, because it's going to be epsilon times this length, but then you have to sum all around. So you get the total length. So epsilon times the perimeter is this up to a little over epsilon. This is true for a small set. Okay? And now just plug it in. Plug in this formula here. So you get the volume of E plus epsilon, the perimeter of E, plus little of epsilon 1 over n, minus the volume of E 1 over n is greater or equal than this. So I take B1 1 over n, and here I divide by epsilon. I just rewrote this inequality using this formula. So I just substitute this with this, and I just apply this here and divide by epsilon. And now you just take the limit as epsilon goes to 0, just a derivative, and this converge computation P n E n minus 1 over n, which is exactly what you wanted. So the Brunn-Minkowski gives you this isoperimetric inequality. Maybe just, okay, there was actually one more thing I wanted to say. Let's see. So I guess that I should stop around. I should be stopped now, right? The time is. You can go for a few more minutes. I can? Okay. Well, I just wanted to show you one more application of Brunn-Minkowski. I mean, there are several more, but for instance, another thing, Brunn-Minkowski tells you, I take a convex set and I start to slice it with hyperplanes, and I want to understand how the volume of the slice changes as a function of the parameter. So let me do just this on the slicing of convex sets. So in the two-dimensional case, this is trivial, and you can just do by hand. So you take a convex set, you take a line, and you start to look. So you take, let's say, T, you take a S, and you look at the length of this segment. You look at the length of this segment, and then you look lambda T plus 1 minus lambda S, some intermediate point, and you look at the length of this. And so you see, in this case, that so if you take the point here and the point here, you do the convex combination. So you take, let's say, every point x here, every point y here, then and you do lambda x plus 1 minus lambda y. This is going to be here. And then you can do it for all points. And so what you get is that, and this, okay, this picture is true actually even in higher dimension, what I'm saying. Okay, let me say general and direct. I mean, the point is that dimension 1 is very easy to see what up. In the dimension 2 is very easy to see what up. But okay, so I have my set. Let me do it this way. I have this, and then take the convex combination, and I can do this for every couple of points. So x and y can be here, or x could be here, and y could be here. And I take the convex combination, and they're always going to end up here. And by convexity, so what you get is the following. So that so if I define ET to be the set E intersection x1 equal t, so this is, let's say, the E1 axis. So this is the hyperplane x1 equal t. Then you know that E lambda t plus 1 minus lambda s contains lambda et plus 1 minus lambda es. So this means that if you take this slice, which is exactly E lambda t plus 1 minus lambda s, contains every point. So this is nothing else than the set of points of the form lambda x plus 1 minus lambda y, where x is here, x is in ET, and y is in S. Right? And it's just a consequence of that picture. And then Brunn-Minkowski tells me that the volume of this is greater or equal than the volume of this 1 over n, so volume of this 1 over n, the volume of this 1 over n plus the volume of this 1 over n. But wait, n now is the dimension of the slice. So here we must be in Rm plus 1. So if we are in Rm plus 1, this is now an n-dimensional set. And this is an n-dimensional set, is an n-dimensional set. And so what I get here is that the volume E lambda t plus 1 minus lambda s 1 over n is greater or equal than the volume of lambda et 1 over n plus 1 minus lambda es 1 over n. But these are n-dimensional sets. So if you take lambda out, since there is 1 over n, so this is a lambda to the n, but then there is 1 over n, so you get lambda. So this is lambda et 1 over n plus 1 minus lambda es 1 over n. So the corollary is that the function which to t associates the volume of et 1 over n is concave. So whenever you utilize a convex set in every direction, you get always that the volume to the power 1 over n is a concave function of the parameter. This is a several application actually in probability and statistics. Then Brunn-Minkowski can be used also to prove other kind of inequality of this form, which have application in crystallography, for instance, to study crystals. Would take quite a while. And actually, for example, Brunn-Minkowski, what is also useful is the converse, that Brunn-Minkowski tells you that if you have equality, then you are convex and you are homothetic. Because sometimes maybe you have a problem where you can prove by some mean that you have equality in the Brunn-Minkowski inequality for some object, and then from this you get a characterization. So just to give you an example, one last example by word, is the Minkowski problem, which is the following problem. You give me, so Minkowski was trying to do the following. He wanted to construct, he was giving himself, so I don't know how many you saw it, but so if you have a surface, you can define a curvature of a surface, which is just telling you how much your surface is bending at every point. And so for every convex set, you have the curvature. And Minkowski problem was the following. He said, OK, I give myself the curvature, and I want to find a convex set which has that curvature. So he had to construct, given the curvature, so given a convex set, you can compute the curvature. But he wanted to do the opposite. He tells you, if you give me the function as a curvature, can I find a convex set which has that guy as a curvature? And he could solve it at the sum assumption. And then the Brunn-Minkowski allows you to prove the quality, the characterization case that tells you if you have two convex sets which have the same curvature, then actually they are homothetic. I mean, they are the same actually, up to a translation and a rotation. So the curvature for a convex set completely characterized up to isometries, your convex set. And this comes passing through the Minkowski inequality. So I think I'm out of time, so I'm going to stop here. Thanks.
Does anyone have any questions? Okay, thank your speaker again.